Assalamu alaikum. In this video, we will look at this example of application of the precedence diagramming method, which is used for project scheduling. So let's look at the following exercise. So here we have the following. So the project manager has decomposed the tasks for the project and estimated the duration of each task. So the project manager, he has decomposed the project in different tasks. So, and then he labeled the tasks. So we have these labels here. We have tasks from A to H. And also he estimated the duration of each task. So we have the duration in this table here. He also defined the precedence relationships between all the tasks. The precedence relationships means that, like here, for example, we have task B cannot start before task A ends completely, okay? And so on. So here we have task C cannot start before task A ends. Okay, so then he summarized this information in the following table. So this is the information, and what we want is to draw the corresponding precedence diagram. Okay, so let's do this. So we have a task A that can start without any constraints. It can start in day 0. So we'll draw that, and then we have tasks B and C that can start after A. Okay, so we'll draw that here. So this so for each task we will draw this little a little table here, and I'll just copy this so that I can duplicate it. So this will be for task B. Okay, so task B will come after task A. Then this will be for task C, and then we have so I'll write down here the labels or the names of the tasks. So this is A, this is B, and this is task C. Task A has an estimated duration of 3 days. Task B, task C have an estimated duration of 2 days. Then we have task D, which comes after B, and then we have E and F that come after C. Okay, so I'll draw this. So this, sorry. So this will be task D, I think. This will be F, and this will be E. Okay, so I just take this here now because with this software so then I will have task G and H. Okay, so I still need this one. Okay, so this will be task D. I have to select the pen. So this will be task D, this will be task E, F, and then we have let's look at the precedence relationships. We have E and F after C, we have D after B, then we have G after D and E. Okay, G will be after D and E, and then this will be task H, and task H will be here. So this will be, this is G, this is H. So we said that task B comes after A, task C also, task D comes after B, task E and F come after C, then task D and E, task G comes after D and E. So we need to wait for D and E to finish in order to be able to start task G, and finally task H can start when G and F finish. So let's write down the durations. So we have 3 for A, 2 for B and C. So the duration of each task will be written in this cell here. So we have 3, 2, 2. And then we have 4 for D, 1 for E, 2 for F. 4 for D, 1 for E, 2 for F. Then we have 4 for G and 3 for H. 4 for G and 3 for H. Okay, so now let's go back to the questions. So this was the first question. Draw the corresponding precedence diagram. So we have drawn the corresponding precedence diagram. Now we want to calculate the 4 parameters: early start, early finish, late start, late finish for all of the nodes. Okay, so I'll write the early start in red. So the early start need to be written here. So we need to start from the first tasks to be able to find out or to compute the early start and early finish values. So early start means that this is the date, the earliest date this task can start. So this task can start at day 0. So we will write down here 0. So this task can start at day 0. And the earliest date this task can finish is 0 plus the duration of the date. So this will be 3. Now, task B can start right after A finishes. So it can start at the earliest date it can start is 3. So it cannot start in day 2, for example, because A is not finished yet. So we need just to report these dates or this date here. Now we just need to add the duration of task B to find its early finish date. So this will be 5, and this also will be 5. Same thing here. Task D can start at day 5, and of course this is the earliest start date and the earliest finish date. Now for E, the earliest start date is 5, the earliest finish is 6. For F, the earliest start is also 5, it can start directly after C, and the earliest finish is 7, which is 5 plus 2. Now what about G? G here is the successor of 2 different tasks. So when can we say that G can start? What is the earliest day G can start? Can it start? Can we start G when we finish E at day 6? We cannot, because G cannot start before D finishes. So we need to take the maximum between all the predecessors of G to know when is the earliest date it can start. So it will be 9. Cannot start before the day 9. Now it will here it can the earliest date it can finish is 13. What about here? What about H? For H, also here we need to take the maximum. So the maximum is 13. So this is the earliest start date, and the earliest finish date is 16. So H, because it's the last activity here, we can say that the project can finish in 16 days. So we will write down here the latest finish. So we want the latest finish to be also 16. Okay. So now we will compute the earliest, the latest finish date and latest start date for each activity. And for this we need to go backwards. We need to start from the last task, which is here. So the latest finish date for H is day 16. So the latest start date will be 16 minus 3, it will be 13. So now, what is the latest finish date of G? Which means that we should not delay G more than this date, otherwise we will delay all the project. So it will be 13. This is the latest finish date of G. So here we have to subtract the duration of G to find the latest start date, which will be 9. For F, the latest start date is also 13. Sorry, the latest finish date is 13. We cannot finish this task after day 13, otherwise we will delay the, activity or the task H, which will delay all the project. So here we have to compute the latest start date of H. So we can start activity F at day 11. Even if we do this, we will not delay task H. So we will not delay the project. What about G now? Now, for G, we will do the same thing. We will just copy the finish, the latest start date of its successor, and here we will get 5. So here we get 5. 5 minus 2 is 3, and here we will get 3. 3 minus 3 is 0. Okay. I'll go back to that later. Maybe this is not correct 100%. So this will be 8. Now here, this task, when should it finish at last? It has to finish before or maximum at day 8. Otherwise, if it finishes later, let's say for example day 9, it will delay this task. Okay, so it will not delay this task, but it will delay this one. So we need to take the minimum here. So here we'll write 8. 8 minus 2 is 6. Okay, now what about this task here? So here I have written 3, but maybe this is not correct. What about this task here? Can we delay this task at day 4, for example? No, we cannot. Otherwise, we will delay this task here. So it has to be, so the latest finish date of A is 3. 3 is the minimum between the two latest start dates of the two successors of A. So now we have found the latest finish date and latest start date of all the tasks. So what we can do now is to find out about the critical path. So the critical path is the sequence of tasks that we cannot in which we cannot delay any activity for any period of time. So here, for example, we can see that the earliest start date is the same as the latest start date, which means that this task here we cannot delay it at all. So this is a critical activity, and we'll see that it's on the critical path. So also this task here, because the earliest start date is the same as the latest start date, which is 3 here. So this is also on the critical path. It's a critical activity. Also G here, and then also G, and then also H. So this sequence here corresponds to a critical path. So the critical path here is A, then B, then D, then G, then H, which means that any activity here, if we delay it by only 1 day, this will have as a result to delay all the project by 1 day. Okay, so now we will compute another value, which is the total float and the free float. So the total float is a variable is a variable that we will compute for each node, and it means the following. It is the period of time we can delay that task without delaying all the project. So it's clear that for the critical path, they all will have a total float of 0. The total float, we will be writing it here. Okay, so the total float is the late start minus the early start. The late start minus the early start. So here the difference is 0. Here the difference is 0. Here the difference is 0. Also here. And also here. So it's the late start minus the early start, or also the latest finish minus the early finish. For this task here, so we can see that the difference is 3. So we can delay this activity by 3 days without delaying the final task. We can see that, for example, if this task is delayed by 3, we will get it will finish at day 8, and then this can start at day 8. Then we'll have 9 here, and then this can start at day 9, so we will not be delaying this task. And also here, we will not be delaying this task. Also, this task can be delayed by 3. 8 minus 5 is 3. And here, 11 minus 5 is 6. So this task can be delayed by 6 days. Of course, these are not, I mean, we cannot accumulate the delays, which means that if this task, instead of taking 2 days, takes 5 days, which means it is delayed by 3 days, for example, for any problem that happens, it takes 5 days. And then if we also here delay this task by 3 days, for example, if it takes 4 days, we'll be delaying E by 6 days. Okay, so this will cause the project to be delayed. Okay, so these values here should not be cumulated, which means that either we delay this task by 3 days or this one by 3 days. We cannot delay both of them by 3 days. Okay, so the next value we need to compute is the free float. The free float is the amount of time we can delay an activity without affecting the successors of this activity. Okay, so we compute this by subtracting. So here for activity A, we need to subtract the minimum of the early start dates here. The minimum, we subtract from it the early finish of the activity, or we can also compute it by subtracting the early start and the duration from the early finish, the minimum early finish of the successors of A. So here the minimum is the same, it's 3, so we need to subtract 3 from 3, so we'll get 0, which means that this activity cannot be delayed at all without affecting at least one of the successors of this activity. What about B? So here we have 5 minus 5, also 0. Of course, for the critical path, we'll have always 0. So 9 minus 9 is 0. Here 13 minus 13 is 0. For the latest activity, this number doesn't have any meaning because this date doesn't have a successor. We can write 0 here, or also we can leave it empty because it doesn't mean anything according to the definition. So here we have 5 minus 5. Also, this is 0, which means that if we delay this activity here by 1 day, we will be delaying this activity by 1 day. What about this one? What about E, for example? Here we have 9 minus 6, which is 3. So we can delay this activity by 3 days without delaying this activity. And what about this one? So we have 13 minus 7. This is 6. So here we can delay this activity by 6 days without delaying this activity. Okay. So these are the values that that we need to compute, and I think we can stop at this point. Thank you.